All right, folks. So what today's lesson is going to be involving, it's going to be, I like to call it a little bit of old with a little bit of new. Back in Algebra 2 and back in pre-calc, you studied your exponential functions and you studied your logarithmic functions. One part of the unit when you were studying exponential functions is you studied exponential growth and exponential decay. You may remember that lovely formula PERT, P-E-R-T. Again, PERT was dealing with compounding interest, money growing over time. So before we talk about the differential form, let's take a look and review the formula PERT for a minute. When you studied PERT, if you remember what that formula looked like back in Algebra 2, the formula we're going to be working with is PERT. It's just got different variables. PERT only deals with the variables that represent money. P, when you looked at PERT, was your initial deposit or the initial amount that you invested. We're going to be looking at C times e to the kt power, which is PERT. C is your initial amount. It is your P. It's your initial amount, maybe initial amount of flies, initial amount of fish that are in a lake. We're looking at a lot of times population growing or decreasing over time. So the C is that initial amount. You have your little e. Notice in the exponent in both formulas, you have a t, which represents time. But R in your PERT formula represents interest rate, which only applies to money. So we use what's called a K, and K is your proportionality constant. In other words, what that represents, it's your growth rate of growth or rate of decay. That's what the K is. So C is your initial amount, little e, raised to the kt power, very equivalent to PERT. Again, how we know the difference between growth and decay. If you're dealing with exponential growth, your constant, your K value is greater than 0. If you're dealing with decay, K is less than 0, be a negative number. So if something's decaying over time, you'll have a K value that's negative. Again, when you're talking about, for example, the value of a car, we know that cars depreciate over time. It would be an example of an exponential decay. So again, something that you're familiar with. Now let's take a look at the differential model. Again, because this is representing differential equations, if I was to take the derivative of C times e to the kt, it would give you this particular function right here. Notice there is that direct proportion that we talked about before break. Again, when we talk about directly proportional, remember the formula is y equals k times t. You have to have that constant of proportionality anytime you're talking about that direct variation or directly proportional. So when we look at the differential form, again, when you're reading these word problems, that's what we're going to be tackling after break. You have to look, are we talking about the rate of change, or are we just talking about the amount of the population? Which formula you're going to use, it depends upon what's given to you in the problem. Again, anytime, remember, you see that word rate of change, we know that we need to be using our differential form. You do have to know both formulas. Both formulas you do need to know. All right. Now, if you do forget, if you have your dy dt is equal to k times y, you can algebraically and through calculus now, you can go back to get this C times e to the kt formula. And this is also a good review of what we did before break, aka separation of variables. Remember, if I want to integrate to figure out what this function represents, I have to separate my variables. Remember, I want to get my y's and dy's on the left, my t's and dt's on the right. So I'm going to divide by y and multiply by dt. So dy over y is equal to k times dt. So remember, if I have this particular differential form and I want to solve for y, remember, we solve these differential equations by using that separation of variables. Now, do you remember what we're going to do to both sides of the equation? We're going to integrate. So what is your integral of 1 over y dy? The integral of 1 over y dy is going to be the ln of y equals. Remember, k is a constant, so I can pull out that constant, and I'm going to integrate dt. So how do you integrate dt? The integral of dt is just going to be what? T. So I have k times t, and don't forget to add your c. Some of you forgot to do that on the last test. When you did your separation of variables, you forgot to add the C. So now remember, we want to solve for y. Right now, y is trapped inside the natural log. So what am I going to have to do to both sides of this equation? I'm going to have to raise both sides to the base of what? E. Because e raised to the natural log of y is just y. Equals. Remember, when you see an addition sign in your exponent, when you see that plus sign, remember, when do you add exponents together? You add exponents together when you multiply like bases. So another way to write e to the kt plus c is e to the kt times e to the c. And again, what is e to the c? E to the c is just a constant. It's just a number. So another way to write this equation would be y is equal to c times e to the kt. So you've got, remember, your differential form for exponential growth and decay. You've got your formula, your actual function for exponential growth and decay. And these are the two equations we'll be working with in this particular section. All right. When we're looking at these problems, regardless of what formula we're using, it's typically always going to be the same process. We're going to always start, when we're looking at these particular formulas, you're always going to start, you're going to have to find your C value. A lot of times they're not going to give you the C. They're not going to give you that constant of proportionality. You are going to have to find it yourself. So the first step when you're approaching these problems, if it's not given, if C is not given to you, the first thing you want to do is you want to find your C value. Then what you're going to want to do is you're going to want to find the K. So before you can actually answer the questions, you're going to have to do some work on your own. That is, you're going to have to find C, have to find K. Very rarely do they actually give you those two pieces. Then once you know C and you know K, you can actually write your equation and you can answer the question. But if they don't give you C and they don't give you K, you're going to have to find them before you can actually answer the question. So pretty much all the problems, this is the steps we're going to follow. You find your C, you find your K, and then you're going to answer the question. So let's take a look at example number 1. And then you also have to make sure you identify, am I going to be using the differential form or am I going to be using the function, the C times e to the kt? So let's take a look at example 1. The rate of change of y is proportional. So there's a key phrase, rate of change is proportional to y. So again, are we talking about rate of change or are we talking about an amount? Rate of change. So right away, I know I'm going to use the differential form, the dy over dt is equal to, again, we talk about that proportional, direct proportional. It's going to be k times y. So you want to identify what formula you're actually going to be using. Is it the y equals c times e to the kt, or is it the differential form? Again, because we see that phrase rate of change, I know I'm going to be using the differential form. Now, when I take a look, they're also going to have to give you two sets of ordered pairs. They may not be, hey guys, this is an ordered pair. You may have to interpret it based on some information given. They're telling you when t is equal to 0, y is equal to 2. So that's your first ordered pair. So I have an ordered pair of 0, 2. Then they're telling you when t is equal to 2, y is equal to 4. So there's another ordered pair. They want me to find what is the value of y when t is equal to 3. So they want me to actually calculate the value of y. They're not talking about the rate of change of y. They're talking about what is the value of y. So what I'm going to have to do then is I'm going to have to use my formula y is equal to c times e to the kt. If you did not remember what that formula was, but you remember the differential form, you'd have to go through separation of variables and you'd have to come up with it. The purpose of them telling you the rate of change is proportional to y. It's so you know you're dealing with exponential growth or exponential decay. Exponential growth and exponential decay, remember, when they told you the rate of change is proportional to y, that's the particular formula. This is my exponential growth or exponential decay differential formula. So they may not be as obvious sometimes when they tell you that this is exponential growth or decay. But to answer the question, I want to know what the value of y is. So I know that I'm going to have to be using this formula to actually calculate a y value. So like I said, the first thing we're going to have to do is we have to find the c value. So when you want to find C, remember C is that initial amount. So when you want to find C, again, you're going to have to use one of the two ordered pairs that's given to you. You want to use the ordered pair where that T value is equal to 0. So I'm going to use 0, 2. So anytime you want to find that C value, you want to make sure you're using the ordered pair where T is equal to 0 if possible. So what I'm going to do then is I'm going to take out my T, take out my Y, and replace it with a 0, 2, and I'm going to solve for C. So I know that 2 has to be equal to C times E raised to the K times 0 power. And again, e to the 0 is just 1. So what's C equal to? C is equal to 2. So now we can start writing the equation by replacing 2 into my particular function for C. So Y is equal to 2 times E raised to the KT. So my second step is now I'm going to have to find K. They gave you two ordered pairs for a reason. That first ordered pair we used to help us find C. We're going to use now the other ordered pair 2, 4 to help us find K. You can't use the 0, 2 again because by plugging in 0 for T, you get that K value to cancel out. So you have to use that other ordered pair so that you have a K to solve for in the equation. So I have 4. I'm going to set it equal to the equation. I've already plugged the C and I plugged in the 2. 2 times E raised to the K times 2. Don't be alarmed. You're going to end up with ugly K values. The K values are not going to be pretty. This is where all the logs are going to come in again. You're going to have to use logs because you're going to be solving for an exponent. So remember, before you take the log of both sides of the equation, you want to get that E by itself. So what's going to be the first step? I'm going to divide both sides by 2. So I end up with 2 is equal to E to the 2K. You've got to make sure before you do the log of both sides that the coefficient of E is 1. You've got to get that E by itself. Now you're ready to go ahead and take the natural log of both sides. So I'll have the natural log of 2 is equal to the natural log of E to the 2K. And again, we've talked about this. Again, what happens on that right-hand side when you have natural log of E to the 2K? What are we going to be left with on the right-hand side? We'll be left with a what? 2K. So I have the natural log of 2 is equal to 2K. So what's K going to be equal to? K will be equal to what? Natural log of 2 over 2. Remember, another equivalent way to write this would be 1/2 times the natural log of 2. So there's your K value. So any questions on how I found K? So now I can start writing the equation so I can answer the question. So now my equation is now going to be Y is equal to 2. That's the C value that I found times E raised to that 1/2 times the natural log of 2 times T. So any questions on the finding the K or finding the C value? Particular question. So again, now the question, remember, is asking us, we want to find the value of Y when T is equal to 3. So now what I'm going to do is I'm just going to plug 3 in for T. So I have Y is equal to 2 times E raised to that 1/2 times the natural log of 2 times 3. Now with these problems, folks, these could be calculator or these could be no calculator questions. If this is a no calculator question, this is your final answer. There's nothing more you can do with it. This is your exact form. So if they want the exact answer, there's nothing more that you can do than plug in the 3 for T and leave your answer alone like that. Because these can be calculator or no calculator questions. Now let's take out our calculators and suppose we want to actually convert this into a decimal. Now, the one thing I want to make sure you are aware of is the K value. You will never, ever, ever take K, put it into a decimal form, and then plug it into this particular formula. You're taking a rounded answer, you're putting it into an equation to round another answer. You are getting further and further away from what the actual answer is. You must always leave K in exact form. Now, this is where we're going to use that store button on the calculator. Remind me again, what mode will my calculator always be in calculus? Radians. We're always going to keep it in radian mode. So double check your modes, make sure you're in radians. So now what you're going to do is you're going to take the K value, which is that 1/2. So I'll take the 1 divided by 2, multiply it by the natural log. The natural log is located right next to 4. And there's your natural log of 2. There's this button right next to number 1, which is called STO. This is your store button. So what we're going to do is we're going to store that particular K value. You can store it in for any letter of the alphabet that you want. If you hit alpha, you'll see on your calculator keypad, you have the whole alphabet. The quickest variable to, the quickest letter to store it in for is X. I'm just going to hit X and then enter. Your calculator has a lot more decimals in its memory than what it's showing. So what's going to happen now by using that store button, anywhere you type in an X just on the home screen, it's automatically going to substitute in that 1/2 times the natural log of 2 for you. So you don't have to worry about typing it over and over again. It's very easy too to make a very careless mistake when you start plugging these into these exponential equations and putting this in as an exponent, maybe make a careless parenthesis mistake. So it's going to help prevent that. So now I can just go ahead and type in 2. Remember, E is under the second ln, raised to that K value, which I've got stored in for X, times 3. So there's my approximate answer. Remember, you will always round to always a bare minimum of 3 decimal places. More is always better, but the bare minimum is you'll round to approximately 3 decimal places, so 5.657. Right here. So this is approximately equal to about 5.657. Gosh, I'm having trouble writing today. Gosh, let me try it again. 3 times the charm. 5.657. Again, this is your approximate. Okay. So like I said, if it's no calculator, what I boxed with a star, that's your exact. That's all you can do with it. The minute you pick up your calculators and you round it, you no longer have exact, you have an approximation. All right, but if they ask you for exact, then that's all you do is you write your equation, plug in that 3. Okay, so any questions on that particular example? Like I said, the whole purpose in this original example, when they tell you the rate of change is Y is proportional to Y, is so that you know that this is the equation that represents this particular model. And they want you to make sure you recognize that this is your exponential growth or exponential decay differential equation. Okay. Now let's take a look at some examples. Like I said, you're going to be dealing with a lot of word problems when you're dealing with these growth and decay. Half-life is a big application. You may have done some half-life back in your chemistry or back in your physics classes. Again, with half-life, what that really means is if let's suppose right now I have 10 grams of salt. And they tell me the half-life of salt is 7 years. So that means in 7 years, my 5 grams would go down to 2.5. So again, that's what your half-life is. A lot of radioactive material has a half-life. If you take a look at uranium, that's why uranium is such a, there's a lot of issues with that uranium because notice how long it takes to get half of the initial amount of uranium to decay to half of its original amount. You don't have to know this, but just from information. And again, back in 1986, there was that radioactive disaster out in Chernobyl. So let's just suppose that 15 grams of the cesium isotope was released during the 1986 Chernobyl nuclear accident and it absorbed into the groundwater. How long? So right away, what does that tell me I'm going to be solving for? I'm going to be solving for T. I know that. Will it take for the 15 grams to decay to 1 gram and become safer to drink? So right away, I know that because they're using that phrase decay, I'm dealing with an exponential growth, or in this case, exponential decay model. Now, we've got to decide what formula we're going to use. Is it the differential form or is it going to be my function form? Does anywhere in this couple sentences, does it state anywhere about a rate of change? No. So right away, I know I'm going to be using my formula y equals c times e to the kt. Now, I also know that the steps are going to be the same. I'm going to find C, find K, and I'm going to answer the question. I have to have 2 ordered pairs. So when you're dealing with these real life scenarios, it's not as obvious what the ordered pairs are going to be. But notice they're telling you that 15 grams of this material was released initially. So at time t is equal to 0, I know that 15 grams of this substance was released into the groundwater. So there's 1 ordered pair, 0, 15. Now in the chart, notice they're telling you what the half-life of this material is. The half-life is 30 years. So what that tells me is that in 30 years, I'm going to have half of the initial amount. So what is half of 15? Half of 15 is what? 7.5. So there's your 2 ordered pairs. So it's going to take 30 years to have that half that initial amount. So those are the 2 ordered pairs we're going to use to help us find C and help us find K. Any questions on how I identified the 2 ordered pairs? So like I said, first step is always the same. You're going to find C. Remember, to find C, you're always going to use C as your initial amount. So you're always going to use the point, the ordered pair that has your T value of 0. And then remember what I'll do is I'll plug that into my exponential decay model. So I know that 15 is going to be equal to C times E raised to that K times 0. So what's C going to be equal to? C will be equal to 15. So I can start writing my equation. Y is equal to 15 times E raised to the KT. So now, again, my second step is going to be to find K. So I'm going to use that second ordered pair of 30 and 7.5. So again, I'm going to take these values, plug them into the equation where I plugged in the 15. So 7.5 is equal to 15 times E raised to the K times 30. What's going to be my first step? I'm going to do what? I'm going to divide both sides by what? 15. So I end up with 7.5 divided by 15 is just going to be a half. Equals E raised to the 30K. Go ahead and solve for K for me. K. So like I said, now that we know C, now that we know K, we're on that third and final step. Now we can write the equation. Y is going to be equal to 15 times E raised to the 1 over 30 times the natural log of a half times T. Now let's talk about, we mentioned that the questions now we're ready to actually answer the question. How long? So right away, what variable am I going to be solving for? I'm going to be solving for T. Again, I'm going to be solving for another exponent. So guess what, guys? We know we're going to be doing logs again. How long will it take for 15 grams to decay to 1 gram and become safer to drink? So I'm going to have to take this equation. I'm going to have to set it equal to 1. So 1 is going to be equal to 15 times E raised to the 1 over 30 natural log of a half times T. What's going to be my first step? Again, before you do logs of both sides, you have to do what? Divide both sides by what? 15. So 1 over 15 is equal to E raised to the 1/30 natural log of 1/2 times t. Now we're ready to go ahead and take the natural log of both sides. So I'll have the natural log of 1/15 equal to, again, natural log of e is going to just cancel out. So I'm left with 1/30 times the natural log of 1/2 times t. Again, this could be a no calculator question. So if I was to divide now by t, my t value is going to be equal to the natural log of 1/15 divided by 1/30 times the natural log of 1/2. Again, this would be exact form. So if it was a no calculator question, I know it looks like a 1/5, but that is a 1/15 there. If this was a no calculator question, your answer, this is it. By the way, what's my units here? If I'm solving for time, make sure you include units. I'm going to be dealing with years. Make it 30 if you want to. But again, if it's free response, don't touch it. You don't need to. So now for the approximation, again, still store your k values. So again, my k value is going to be 1 divided by 30. So on my calculator, I'll take 1 divided by 30 times the natural log of 0.5 or 1/2. Remember, the store button is located right next to 1. I will hit X and then enter. Notice you should get a k value that's negative because it is the k. So when you're using that store feature on your calculator, that previous X value that was stored in, it's overridden. The only place your calculator will plug in these values is on the home screen. If I wanted to graph and I typed in like y equals x squared plus 3 and I want to look at the graph, when you go to your y equals, it's not plugging in the value for x on that screen. It's not hurting your calculator or anything by having it on your home screen. So now I'm ready just to go ahead and type in the natural log of 1/15. And since I stored this value in for hex, when I hit divided by, all I have to hit is the X and then enter. So it's going to take approximately 117.207 years. So it'll take about 117.207 years for that groundwater to be safe to drink where that nuclear accident was. I'm not going to use the differential model example 4. I'm going to be using the y is equal to c times e raised to the kt. Nowhere in there do I see something about rate of change. Now, the next thing you want to do is identify the ordered pairs you're going to use. So the manufacturing company notices the sales have dropped from 100,000 units to 80,000 per units. So my first initial amount is going to be 0, 100,000. 4 months later, the company noticed it dropped to 80,000 units per month. So I know my second ordered pair is going to be for 80,000. If the sales follow an exponential pattern of decline, what will they be to the nearest unit after another 2 months? So I want to find y when what? When t is equal to what? Be careful. It's not 2. It's going to be what? 6. So did everybody come up with 100,000 for C? Okay. So now my second step, remember, is I'm going to find K. Remember, this is where I'm going to use that other ordered pair, the 4, 80,000. So everybody go ahead and find K for me. So now that you have that K value, remember, now you're ready to go ahead to write the equation and answer the question. So Y is going to be equal to 100,000 times E raised to that K value of 1/4 times the natural log of 4/5 times T. And again, remember, we want to now answer the question. We want to find Y when T is equal to 6. Now, when they say what will they be to the nearest unit? Right away, you know this is a calculator question. Or they say round, or they say to the nearest unit, you know that it's going to be a calculator question. So you can use your calculators to go ahead and answer that question. 71,554 units. And again, it says to make sure you round it. So, okay. So any questions on these exponential growth or decay before we take a look at a little twist of one? Go back to example 3. All right, the reason why I went back to example 3 is because there's a little bit of twist on example 3. So let's take a look at example 3. So we have a graduate student talking about population of fruit flies. She works under the premise that the experimental population increases according to the law of exponential growth. So again, right away, I know I'm going to be dealing with those two formulas. She counts 100 flies after the second day and 300 flies after the fourth day. However, she forgot to record the number of fruit flies initially she had at the beginning of the experiment. Approximately how many flies were in the original population, round to the nearest fly? So in this particular case, I'm not solving for time, and I want to know how many fruit flies were in the original population. First of all, let's decide what formula. Do I see anywhere in here about a rate of change? No. So it's going to be it's going to be y equals c times e to the kt. So I know right away I'm using that formula. Which variable are they actually asking me to solve for? C. So I need to find C. Still going to follow a very similar process that I did in all the others. I need to identify my two ordered pairs. Well, I know that she counted 100 fruit flies after the second day. So I know that one of my ordered pairs will be 2, 100. And then after the fourth day, she had 300 flies. So I know another ordered pair is going to be 4, 300. So any questions on how I identified the two ordered pairs? Now, what I'm going to have to do is I know that I'm going to have to solve for C eventually. So what I'm going to do is I'm going to use both ordered pairs, and I'm going to plug them in, and I'm going to solve this equation for C. So I'm going to treat this just like finding C. So I'm going to take 100, set it equal to C times E, raised to the K times 2 power. So I want to solve for C. How would I solve this for C? To get C by itself, I would divide both sides by e to the 2k. So C is equal to 100 divided by e to the 2k. Unfortunately, this is a case where the k value doesn't cancel out. I don't know what the exact number is going to be for C just yet. So I am going to have to use my second ordered pair, plug it in, solve for C again. So again, I'm going to take my 300, set it equal to C times e raised to the 4k. I'm going to solve for C. So C is going to be equal to 300 divided by e to the 4k. So notice my first step was still to solve for C. It's just I don't exactly have a numerical answer for C just yet. The second step of all these problems have been to find K. This is going to go back to systems of equations that you studied back in Algebra 2 or Algebra 1. Remember, wouldn't you agree with me that C has to be equal to itself? So I'm going to take these two equations that I already solved for C, and I'm going to set them equal to one another. So I'm going to take 100 divided by e to the 2k, set it equal to 300 divided by e to the 4k. Because we've already done an example where we solve for the t. We've done an example where we solve for y. Now we're doing an example where we actually have to solve for C. These are just different ways of solving for the different variables in this equation. How do we solve this? What are we going to have to do? This was actually on Jeopardy last night. Do you know there was a math category on Jeopardy last night? Cross product is what they called it. I was like, oh, I know that answer. 100. I always get excited when I know an answer on Jeopardy. 100 e to the 4k is equal to 300 times e to the 2k. So what I'm going to do next is I'm going to divide either by 300 or divide by 100. I would rather divide by 100 so I don't deal with a fraction. So I have e to the 4k is equal to 3e to the 2k. Now I have an e on the left and an e on the right. So I want to bring that e to the 2k over. So I'm going to divide both sides by e to the 2k. So I have e to the 4k divided by e to the 2k is equal to 3. I'm dividing like bases, correct? Because they both have a base of e. So when you're dividing like bases, what's your rule for exponents? You're going to subtract. What's 4k minus 2k? E to the 2k is equal to 3. Go ahead and finish and solve for k for me. Half times the natural log of 3, that's the k value. So now remember, the process is very similar. It just looks a lot different than the other two examples. We found c, but we had to solve for c. Then we found our k value. Now we have to write our equation and we have to actually answer the question. So again, my equation is going to look like this. Again, in order to find c, I'm going to take that k value, plug it in. It doesn't matter which one you plug it into. But to actually answer the question, the equations are written for you in a different format. What you just simply need to do, it doesn't matter, eeny, meeny, miny, moe, take your k value and plug it into one of those particular equations. So go ahead and answer that question for me. Do we end up with 33 flies? So there we go. So that's how so we know initially we had 33 flies. So any questions on so we did an example we had to solve for t, we did an example we had to solve for c, and then we had an example where we actually just solved for y. Okay, so any questions on that? All right, we're going to come back and do example 5 on Monday when I see you, but let's go back and take a look at this local linearization. We actually did a lot of this back in unit 3. It's a fact. This is a very good review. We did this with L'Hopital's rule. We did local linearization all the way back in unit 3. The only piece that I'm adding in here with the part we did not discuss was whether or not when we did these approximations, were they over or under approximations? Remind me again, how do we find, what does the second derivative tell us about a function? It tells us what? You remember? Concavity, exactly. And that's how we're going to know whether or not when we do our approximations, if they're over or under, we're going to be looking at the concavity, which means we're going to be looking at the second derivative. And if you remember, when we did our linear approximations, if we zoom in on a graph at any point, it looks like a line. So when we did our linear approximations, remember we started by writing the equation of a tangent line. Notice the picture that I'm giving you, this tangent line that I'm giving you right here is above the curve. That happens when your curve is concave down. So when we are looking at whether or not our approximations are over or under, if it's concave down, the tangent line is going to be above the curve, which means that when you look at a point on the line, we have an x and a y value. When you look at the same x value on the curve, this y value is going to be less. So we know that if it's concave down, then my approximation I'm going to use from the tangent line is going to be an over approximation. The y value would be bigger. So just to review what we did with our local linearization, how we did the approximations. Remember what we did was we wrote the equation of our point slope form, the y minus y1 equals m times x minus x sub 1. So we found these approximations using the tangent line. We first write the equation of the tangent line. Then we took the equation and we solved for y. So y is equal to y sub 1 plus m times x minus x sub 1. So when we actually write L of x, we're talking about the linearization. So we know that the linearization is going to be y sub 1 plus m times x minus x sub 1. They may use a different phrase. They may say that this is use a local linear approximation, or they may say use the tangent line for the approximation. The process is exactly the same. So just so you know, they may ask it in one of those two formats. So we do find L of X is our linearization. So this is all what we did back in Unit 3. We wrote the equation of a tangent line, we solved for Y, and then what we actually ended up doing is plugging in a value for X to get an approximation. What's new is the estimation. When your graph, and this was illustrating the picture, you're going to have an overestimation. An overestimation is going to occur when your graph is concave down. That's when you have an overestimation. So if your graph is concave down, I'm going to call that f of x. No matter where I put a point on this curve, and I sketch my tangent line, the tangent line is going to be above the curve. This is my linearization. This is the equation of the tangent line. So you can visually see how the tangent line is above the curve, and these y values are going to be greater than what's on f of x. So this is how I know that my approximation of L of x is going to be greater than f of x. Now we talked about the second derivative in concavity. What happens with the second derivative? How do I know I'm concave down looking at the second derivative? Is the second derivative positive or negative? Going back now to Unit 5, negative. So remember, if f double prime of x is less than 0, remember your graph is concave down. So what we're going to have to do is figure out when I plug in this particular x value into the second derivative, because I want to know what the concavity is going to be at the point that I'm using for the tangent line. So I need to figure out whether it's concave up or concave down at that point. My underestimation occurs when the graph is concave up. So again, if I have a graph that's concave up, I'm going to call that f of x. And I write the equation of a tangent line at a particular point. There's my L of x. You can see what happens. The tangent line is now below the curve. So when I'm using the tangent line, I'm using the y values on the tangent line to come up with an approximation for f of x. You can see those y values are less. So what happens is your L of x is less than f of x. Again, you're still going to have to look at the second derivative. Remember, to be concave up, your second derivative is going to be greater than 0. So this is when your graphs are concave up. So again, we have to know what's happening at the concavity at that point on the tangent line. So like I said, we did the linearization back in Unit 3. The part that's new is whether or not the over or underestimation. Let's take a look at example 2. Find the local linear approximation of L of x for 2x to the third minus 3x at x sub 0 is equal to 1. Use it to approximate L of 0.99. And then they're asking me, is it an over or under estimate? Well, first of all, I have to write the equation of my tangent line. Remind me again, what two things you always have to know to write the equation of a tangent line? You have to know the point and slope. So my point, I know the x coordinate's 1. So what's my y coordinate going to be? My y coordinate's going to be 2 minus 3 is negative 1. Let's talk about the slope. Where does the slope come from? The slope comes from the derivative. So I have to find f prime of x. Now be careful, we've been integrating a while. Now we're back to derivatives. So when I take the derivative of 2x to the third, that's going to give me a 6x squared. Derivative of 3x is a minus 3. I want to find the value of the derivative at x equals 1. So I'm going to find f prime of 1. So 6 times 1 squared minus 3, that's just going to give me 3. So there's my slope. Questions on how I found my point or how I found my slope? So now I have my point. Now I have my slope. I can write the equation of my tangent line. So I have y minus negative 1 or y plus 1 is equal to 3 times x minus 1. So now remember, to find your linearization, remember you're going to take this equation and you're going to solve for y. So I'm going to subtract 1. So y is equal to negative 1 plus 3 times x minus 1. So any questions so far? Now I'm ready to go ahead and approximate. They want me to approximate what L of 0.99 is. 0.99, remember, is my x value that I'm going to plug into that particular equation. So L of 0.99 is going to be approximately equal to negative 1 plus 3 times 0.99 minus 1. Which about negative 1.3. No, I just realized I typed something in wrong. Negative 1.03, yeah, I missed it. Yeah. So like I said, this is a nice review, stuff we did back in Unit 3. Now the new piece, the question is this going to be an over or underestimate? This is where we got to check the concavity. What's happening with the concavity at that particular point, 1, negative 1? So I want to know if I'm concave up or concave down at 1, negative 1. So remember, I'm going to have to find the second derivative to figure out what the concavity is going to look like. So I know my first derivative is 6x squared minus 3. So what's the second derivative going to be? The second derivative is going to be a 12x. And then I'm going to plug 1 into my second derivative. So when I plug in a 1, that gives, you don't have to actually work it out. You just have to know if it's positive or negative. But I knew, though, that this is going to be greater than 0. Draw your U's, folks. What does it mean when the second derivative is positive? Am I concave up or concave down? Up. So what does that tell me then about my approximation? Is it going to be an over or under approximation? Under. So it's going to be an under approximation. And again, when they ask you to justify, it's because your f double prime of 1 is greater than 0 and your curve is going to be concave up.